Welcome everyone. I hope you have been enjoying the sessions so far. In this sessions, we are in this session we are going to learn about how we can build and test the cloud infrastructure using Terraform and leverage Terraform modules to make our lives easy. This talk will have a demo which will be focused on creating some infrastructure on Google Cloud Platform. So let's begin with the talk. My name is Pradeep. I'm an IT consultant with over more than 10 years of experience in various domains like big data, cloud, and DevOps. I hold few Google Cloud certification and I'm also a GDE, Google Developers Expert in the cloud area. Today's agenda for this session is we are first going to talk about infrastructure automation. Then we'll jump into learning about Terraform and then see how we can set up our workstation to use Terraform, how Terraform modules can help us, what are the testing capabilities we have in this ecosystem, and at last we'll do a demo where I'm going to show how to basically test Terraform modules using some of the tools which we're gonna see in the testing section. So what is infrastructure automation? Infrastructure automation is a way to build and manage infrastructure objects using scripts or code with no human or minimal intervention. Some of the benefits of the infrastructure automations are faster deliveries, mean teams can deliver the updates or new features at a faster speed, improved reliability, which means consistent output through automation, meaning if we are trying to create some infrastructure over and over or again and again, we should get the consistent output given the input remains same. Then the cost is reduced. So by removing a lot of manual steps and errors, by removing a lot of manual steps and error, we are basically lowering the cost. And then at the end, it enables teams within the organizations to communicate in a better way and hence increases the collaboration within the team or within the organization. There are multiple tools to achieve infrastructure automation such as Terraform, Chef, Puppet, and Salt. These tools are focused on variety of areas, but the Terraform tools is mostly focused on the cloud infrastructure uh, uh, in the given scenario. So let's learn about the infrastructure as code. So infrastructure as a code is an approach to manage systems or networks or any other infrastructure objects through a source code. Similar how we write and manage applications using Python or Java, in the same way we write or we define the infrastructure using a code, and we can store that code into a version control systems like GitHub, GitLab, or Bitbucket, etc. With the infrastructure as a code, we get these functionality like our code is like our the infrastructure is consistent. We can repeatably create the infrastructure in a given environment or in a multiple environment. We can make changes to the environment or to the infrastructure, and using such tools, it fosters the collaborations between the team. Out of the we looked at several tools like Terraform, Chef, Puppet, Ansible, Salt, etc. So Terraform is a very popular tool within the infrastructure as a code space. So Terraform, it's an open source project backed by HashiCorp. It allows us to build, manage, and version our infrastructure in a very easy way. It has its own configuration language, which is called as HCL, HashiCorp Configuration Language, which is a declarative language. So HCL was designed so to allow users to describe infrastructure in a better way. Also, Terraform release cycles are frequent. So I always encourage you to visit terraform.io for the latest documentation and the latest download. It's an open source tool and it's written in Golang. The GitHub link is here. So you can visit github.com/hashikop/terraform to see the Terraform source code. Now, let's look at some of the features of Terraform. First of all, it's a platform agnostic. What it means is with Terraform, we can manage heterogeneous environment with the same workflow. Like for example, with the same workflow and using the same language, we can manage the resources on Google Cloud Platform or AWS or Azure, or let's say on GitHub itself, like creating a repositories or managing users. All those stuff we can do from the Terraform. And what we need to do is we need to write the configuration as needed. So for example, the configuration for AWS would differ than the configuration with the GCP or configuration with the GitHub, etc. The next important feature of Terraform is state management. It's a very critical or a key feature of the Terraform. State management keeps tracks of all the infrastructure object it creates uh, as defined in the configuration file. And, and all these tracks or all these information Terraform stores in a file, and that file is called a state file. Terraform can also infer dependencies between the different objects. For example, if I'm creating a subnet and a VM inside a subnet, and I'm defining that code in a single Terraform project, Terraform is intelligent enough to know that it has to create the subnet before trying to create a VM. So it will first create a subnet, and then once the subnet is created and available, then only it will try to create a VM. And if there are no dependencies within between the objects, let's say you are creating three different VMs or you are creating a VM and a Google Cloud Storage bucket, then it can try to create those resources in parallel. Another good thing when using Terraform is like after we write the Terraform configuration, we can do a dry run, or that's called as a plan in the Terraform world. So we can execute a plan which helps us to understand what infrastructure is Terraform is going to create, or what changes it is gonna perform, or what resources it is gonna remove based on the configurations we have defined. Then we can also see a resource graph. So resource graph will shows us dependencies in a graphical format. So we can easily understand which resource is dependent on what and etc. And as I mentioned, we have a facility, or Terraform will try to create the multiple resources in parallel wherever possible. So let's say in a Terraform configuration, if you have defined 20 resources and they are not much interdependent, Terraform will try to create them as much as in parallel as possible. It won't do in a like a serial fashion, like it won't do in a fashion such as it will create a resource one, then wait, and then create resource two, and etc. It won't do such thing. It will try to create resources in parallel as much as possible, and we can control the level of parallelism as well with the configurations within the Terraform. Now let's understand some of the core concepts of the Terraform. First of all, we look at Terraform providers. So Terraform providers are the plugins which translate API interaction with the services. For example, interaction with GCP service or AWS service, we have a Terraform provider to interact with those services. It also helps us to authenticate against the service. So when I'm defining a Google provider, it tells Terraform to interact with the GCP services, and also with the parameters I can provide how to authenticate with the GCP services. So it is defined using a provider keyword, and then the provider name. So Google in this example. So if you want to interact with another provider, for example, AWS or Azure or something like that, please check for the provider name into the Terraform documentation or the provider documentation. Then in the provider block, we need to set few attributes. For example, project and region in this example. Again, check the provider documentation for the required parameter to set, or all the parameters you can set for the provider of your choice. For example, if you are looking for an AWS provider, these parameter name could change. If you are looking for Azure, the parameter name would change and the number of parameters or required parameter you need to provide is different. So please check the documentation for the provider you are looking to do that. At the time of writing this slide, as per the Terraform website, there are almost 35 official Terraform providers and more than 200 verified providers available for the Terraform. With that, there are a number of providers written by the community member that are also available to use it. For a full list, please check registry.terraform.io/browse/providers. That's where you can find all the providers which are available within the Terraform ecosystem. And there is a filter to see like what's official provider or what's a verified provider or what's a community member provider. Another core concept in the Terraform world is resource. Resources are the important element in the Terraform world. Each resource block describes one or more infrastructure objects, such as virtual network or buckets or compute instance or high-level components such as DNS record. A resource block declares that we want a particular infrastructure object to exist with a given setting. In this example, we want a Google Cloud Storage bucket with name app configs and in the Europe West 2 region. Sorry. When we write the configuration for the first time, the resources we define in the code only exist in the configuration and does not represent the real infrastructure object in the cloud or in the target platform. When we run Terraform apply, then Terraform starts the process of creating, updating, and destroying the real infrastructure object to make the infrastructure matching the configuration. In this example, sorry. So in this example, the resource type we are defining is Google underscore storage underscore bucket. And then we are providing the attributes like name, location. There are another attributes as well. Again, to see the full list of attributes you can pass for a particular resource, please check that the resource documentation. On the Terraform documentation, you will also find some examples how to interact with that particular resource, which is really helpful. Next is the data source. So data source, next is the data source. Data source allows Terraform to read the information defined outside of the Terraform. For example, I'm creating some resources, probably manually through script or maybe another Terraform configuration. And I want to read that particular information or the ID of that particular resource in my own Terraform code. Then I would be using data source. So data store help us to retrieve the value dynamically. Uh, For example, network team create a VPC on the Google Cloud platform, and we want to get some attributes of the VPC in the Terraform project where I'm creating a VM instance. Let's say the VPC self link, etc. Then instead of hard coding or generating the VPC self link, what I can do is I can use the data source for the VPC and get the VPC self link. Another example could be, for example, I want to use some Debian based image when I'm going to create a VM instance. So instead of hard coding the image ID or which changes whenever there is a new release, I can use the data source and pass certain parameter to say that, okay, I want a Google underscore compute underscore image as a data source. and then providing the attributes, for example, which belongs to family Ubuntu 804 LTS, and it resides in the project, for example, GC hyphen UE FI hyphen images, etc. So that's how we are able to read the uh, the the image ID of that particular Ubuntu image, which is already available. As I mentioned earlier, Terraform state is a very key concept within the Terraform. It stores the information about the infrastructure managed by the Terraform. So when we define some Terraform code, let's say to create a VM instance or like a bucket, etc., once the resource is created, the information like its name, ID, its properties, etc., all these information is stored in a file, and that file is called a state file. By default, Terraform stores this file in a local mode, and hence with a name called terraform.tfstate, and hence it's called as a local Terraform state file. But we can also store these state file remotely on maybe GCS or S3 for better working in a team environment. When you have a Terraform state file in a local mode, it's very hard to collaborate within the team, because the state file lives in your local system and another team player or another team member won't know what resources has been created for that particular code. So hence it's better to use the remote state when working within the team. Also, when you're working alone, if the resources which you are doing for production or critical, it's always good to have in the remote, because if you lose the local Terraform TF state file, then your resources created by Terraform could become off, and then you would probably need to import them one by one, which is a painful task. Now let's understand the life cycle of Terraform. First, we start by writing the code. Let's say we want to create a Google Cloud Storage bucket using Terraform. To achieve this with Terraform, we will write the code in HashiCorp configuration language, also known as HCL. The code would look something like this, what we see in the slide. As we are gonna create some resources in Google Cloud, we first define the Google provider with the details like the project ID, the region, and etc. Then we define the resource block for the GCS bucket and all the required attributes. And additionally, if you want to override the optional attribute, you can provide that. In this example, what I am doing is I'm providing the name as app config 3423421 and the location as Europe West 1. Then the next step would be the initializing the Terraform code. And the command is Terraform init. So you basically navigate to the Terraform code directory, and then we type the Terraform init. What it does, it will initialize the backend. So where you have the local or remote Terraform state. So that it will initialize. Then also it will initialize the provider plugins. So in our example, we are using the Google provider. So it will try to initialize and download that Google provider if it's not available on your local system. Uh, all those stuff it will do, and at the end it will say that the Terraform has been successfully initialized. And when it does, in the log you can see which provider version it is downloading for the particular uh, code. Then we do a dry run, or you can say like executing a plan. For that, we run a Terraform plan command. Once we run the Terraform plan command, we will see the output something like this. Here, what it's showing is it's showing that plus sign, which means it is going to create some resource, which in this example, it's going to create a Google Storage bucket resource. And what are the values it knows? For example, it's going to create in Europe West 1, its name is this, storage class is standard. This was the optional attribute which we left not defining in our code. So it's going to take the default value, which is standard for Google Storage bucket. And then we also see some like known after apply like ID or self-link or URL, etc. So those Terraform will know once it creates a resource. At the end of the plan, it will give you a summary like how many resources it's gonna create or like add, how many resources it's gonna change or destroy. So it's critical to review the plan before applying these changes. Once you are happy with the plan or you have reviewed it, we can run the Terraform apply command to apply those changes. As soon as we run the Terraform apply command, Terraform will try to will start interacting with the cloud APIs and start creating the resources. So as soon as we run Terraform apply, it will start creating, like in this example, Google Cloud Storage bucket. And once the completion is done, it will say apply complete, how many resource added, how many resource change, and how many resource destroyed. And let's say if we no longer need those resources and we want to destroy that particular the resources defined by that particular Terraform project, we can run the Terraform destroy command, and that will start destroying the resources defined by that particular Terraform code. And at the end, it will show you like how many resources are destroyed. In our example, we only defined one resource, which was Google Cloud Storage bucket. And by running the Terraform destroy, it destroyed that particular uh, resource. So this is about the highlight about the Terraform. So if you are not familiar with the Terraform, I hope this have given you some good idea about what is Terraform and how to use the Terraform. Now, to get started with the Terraform on your local system, what it's very easy to get started or set up the Terraform binaries. So if you're a Mac user, you can basically just run like a brew install Terraform, and that should just install the Terraform. Once that brew command is finished, you can just run Terraform -help to see, and you will be able to see all the Terraform command and etc. Or you can run Terraform version command to see what version it is installed. If you are looking more in detail, please refer to my blog, Getting Started with Terraform. That's where you can find how to set up a Terraform on your local system. If you're a Linux user, you can basically get the binary of the Terraform. Please use the latest binary. For now, I think it's 1.3 or 1.2 Terraform is released. So please check the latest binaries or whatever version you want to try out. Another thing is like when working with Google Cloud services, you would need a G Cloud as well on your local system. And to install a G Cloud, you can just run this command to get a G Cloud installed on your system. For more details, please refer to this blog, Getting Started with Google Cloud SDK. I hope all the slides are clear so far. If you have any questions, we will have a dedicated time at the end, so feel free to ask the question at that point of time. Now, let's say this is we want to create some infrastructure, and this is a sample architecture what we want to create. So here, what do we want is we want a web server running on a VM instance, and which can interact with the cloud storage bucket and has a service account attached to it. It's a simple architecture. So you can have this architecture in, let's say you're creating in a dev project. So to create this infrastructure, what you need to do is you would need to define Terraform code. So for example, as you need a storage bucket, you would be defining a storage related component, and you need a service account. So you are defining the service account related configuration. And also uh, we need a VM instance, so we are defining a Google Compute instance resource to create a VM. So we have defined a Terraform code which creates a VM instance using the Google Compute instance resource, uh, a GCS bucket using the Google Storage bucket, And also we are uploading an object using Google Storage Bucket object to that created bucket. And we wanted a service account to be attached. So we are creating a service account, Google service account resource, and then providing a permissions, for example, storage.admin to that particular service account. So this is how the Terraform code would look like for the sample architecture which we have seen. Now, this is good, but the problem is it's good if you are just defining in a dev environment. You just write some code, you get going. But let's just say, or in a real world, you're just not limited to dev. You'll obviously develop in the dev environment, but then you promote your code into various environment. For example, you would be promoting code from dev to test. So you need the same infrastructure in the test environment. Then you need the same infrastructure in the prod environment. Or another scenario could be that you have multiple dev environment and you need the same infrastructure for separate developers or set of developers. So you need to create the same infrastructure in multiple GCP projects. So if we have the code defined in the previous fashion, you would basically be copying the code again and again for each project. Okay, so there is a lot of like a code duplication, and it's not easy to manage because if you have a copy like five different copies of a same code, and if you want to change a code, you would then need to make changes at five different places, which is not a maintainable, which is not a good way to do the development. So that's where the Terraform modules comes into the picture, which will help us. The Terraform module helps us to package the Terraform code in a library format or in a package format. So the analogy would be like, let's say if you are using a Python, right? And you have some function which you are using very frequently. So you might want to just create a library out of it and then use that library in your different applications or programs. Similarly, in Terraform, we can basically package the code in a module format and then we can just call that module. We will see later down the slides and also in the example how easy is to then define the code and read and make changes and etc. First of all, let's just understand what's the Terraform module. So Terraform module is nothing but a collection of different Terraform resource. So for example, in the previous example, we saw like different resources like a resource for creating a VM instance, a resource for creating a bucket, resource for creating a service account, resource for uploading an object to the bucket. So if you just put all these collection, we could create a Terraform module out of it. And it allows to basically create a blueprint. So if we just define that code in a Terraform module, which means we are just defining that architecture which we need, or we're defining the blueprint. And it makes or it helps us to then easily understand the infrastructure. By doing so, we are basically reusing the code. So it avoids the code duplication. And also each and every developer doing their own code, they can basically focus on developing a single module which benefits the whole team or maybe the multiple teams within the organization. There are a lot many modules available in open source as well, which helps a bigger community. So Terraform modules foster the collaboration and it helps us to start quickly. So let's say if you are something new with the GCP or AWS from the Terraform perspective and you want to get started quickly, and you don't have a time to write the code from scratch, so you might just try out some open source available Terraform modules to get started. And with the Terraform module, we can also do the versioning of the code. So when you are adding a new feature to the Terraform module or removing something, you can always version so that the code which is using the module can basically use the right version so that there is no disruptive changes into the infrastructure. In this particular session, we are gonna look at the Terraform modules which I created for the GCS. So you can find on the GitHub. The link is here on the slide. So how the Terraform the code is structured is again there could be multiple ways. This is the way I'm defining, which I find is much more readable. But again, you can take this as a code structure and then you try to tweak it and make a best structure for your particular use case. So, so what you would have is you would I would generally keep the variables, define variables in a file called variables.tf, the outputs in the output.tf, whatever the resource I'm defining in a separate TF file with a meaningful name. So in this example, I'm defining a buckets, GCS bucket. So I have a bucket.tf file, and then with each module, I would prefer to have a change log where I can maintain what has changed within the Terraform module over the time. A README, nice README, which helps the team or the consumer of this module to get started with module easily. And then some examples how to use this module or some examples for this module. And for test, we'll see like we'll have a test directory as well when we're doing test. Now, in the previous slide, we saw a lot of code, a lot of number of lines. I think it was about 50 lines of code to create like which creates a VM instance, then service account and bucket and etc. If you are using the resource directly. If you package those things in a module and now I want to basically create the infrastructure for my application using the module, it becomes very compact. You can see there are like less than 10 lines to create that whole infrastructure. What I'm saying is I've packaged that code in a module and then I can say the module source path is somewhere on the local system, let's say on my modules app, and then providing all the required arguments for my module, or the source can be a GitHub repository on HTTPS protocol, or it could be on SSH protocol as well. I can also define the particular version. As I mentioned, modules can be versions, so I can define a particular version or a tag for that module to use. So this makes a life very easy when defining that infrastructure over and over in maybe in the same environment or in different environment. Or if you want to deploy or create the same infrastructure in a for a different application, maybe with some different name. For example, here what I am doing is uh, I want to deploy the same infrastructure for my app 1 and my app 2. My app 1 infrastructure is created in GCP project 1 with the environment tag as a dev 1, and my app 2 is deployed with the environment dev 2. So I can call the modules multiple times to create the similar type of infrastructure and just passing the right values to it. We saw that modules source can be local path or GitHub, but there are a lot many sources path available. For a full list, please go to the Terraform IO documentation. This is the some of the list which is being frequently used in the community like GitHub, Bitbucket, Terraform registry, S3 bucket, GCS bucket, etc. Excuse me. If you go to the registry.terraform.io, that's where you can find the Terraform modules which are available in open source space. And also you will find the provider details as well. Now, let's see like how the modules can make our life easy. So just to give an analogy, modules you can think of as a building block. You create a building block and then you combine that building block to create a bigger picture. So for example, we in an organization our task is to create the cloud infrastructure on a GCP. So we create a project module, then we create an IAM module, BigQuery, data store, and various other modules, right? Then let's say if you want to create a GCP project, what you do is you just use the project module and create GCP project or multiple GCP project. On top of a GCP project, when you want to create a network, you use the network module. You can have one network or multiple network. To create some BigQuery resources, you can use BigQuery module. To create a compute VM instance, you can use compute module. Or if you are deploying an app which requires a combination of resources, for example, it requires a compute, engine. It requires a GCS bucket. It requires an IAM rule. This is what we did in the previous example. We can do so. So we can basically combine or we can within one application we can call different modules to create a bigger picture. Similarly, on another cloud as well, for example, AWS, you can do similar things. So you can have module for like ECS, IAM, Lambda, DynamoDB, S3, EC2, etc. And you can have like a multiple AWS account, multiple network, Lambdas, app installed using the Terraform. Now let's focus on the testing in the Terraform world. What type of test you can do in the Terraform? Majority, like I've just categorized the test in a 5 different categories. So like one is like the unit test when you develop or write some code, you try to do a unit test, then contract test or like the validation test. Then you can do some testing around the configurations you're writing, and then integration test, how the infrastructure is working with your application, and then full end-to-end testing, which basically tests that whether whatever infrastructure you have created on the cloud uh, works well, you get all the resources which you need, and they are functioning as expected. So when you're doing unit testing, you can do combination of things. So like you could use Terraform FMT command, which basically format the code, makes us the code more readable. You can use the Terraform validate to basically check the configurations or syntax are correct or not without going to the cloud APIs. Then you can also run Terraform plan, which is a dry run, which will make sure that whatever code you have defined can be executed. There could be some edge cases that where Terraform plan is like working fine, but when you do apply and when Terraform tries to connect to the cloud API, there could be some failures. But majority of the errors you can still capture with the Terraform plan. Contract testing, so when you define a variables, you can write some custom validation rule. For example, you define a variable which should only expect some certain values. Let's say you define a variable called environment, and then you only expect certain values like a dev, staging, and prod. You don't expect any other values. So you can have validation for such variable. Then for configurations, there are multiple open source tools available like tflint, checkout, tfsex, sync, snake. So with the help of these tools, we can do like configuration testing, see like how good is our configuration, are there not any bad configurations or security checks which we need to do, etc. In terms of integration testing, you can do with Kitchen Terraform, TerraTest. There could be more tools available, but these are the popular one. Uh, Kitchen Terraform is based on Ruby and TerraTest is based on Golang. And end-to-end test, again, you can try out Kitchen Terraform to do the end-to-end testing as well. For this particular session, we are going to do a module testing on a GCP. So we are going to use these tools like a test kitchen, kitchen Terraform, and inspect GCP. In combination of that will help us to test the resources created by modules on the GCP. So the module, when we write a module and when we define a test, the structure would look something like this. You would have the usual module structure, which we saw earlier. Then after that, uh, you can have a gem file on the root folder, which define or tags the version we are using for the Ruby packages. And then .kitchen YAML file, which defines the configuration about the kitchen. The major thing is the test. Under the test, you have a fixtures where you define the Terraform code, what you actually want to create. And under the integrations, you define the test, what type of test uh, you're gonna do. For example, for this GCS module, what we can do is once the GCS bucket is created, we can check like, okay, if the GCS bucket is versioning enabled, if the name is correct, what we defined in the Terraform, etc. The life cycle is again similar as to Terraform. So first we run the kitchen create command to basically initialize the kitchen environment. then run the kitchen converge, which basically start creating the Terraform, which start basically running the Terraform code and start creating the resources on the cloud. Then we run kitchen verify, which basically runs the test and see like what all tests pass and what all tests fail. And once we are done with this, we can run the kitchen destroy, which will basically clean up uh, the whole cloud infrastructure created by this kitchen, and so that we don't get charged. We are gonna do this in a demo, but again, if you do in your own Google Cloud account, uh, please be aware that based on the code which you define, there could be some charges to your Google Cloud account. So please make sure that you're aware of that. The source code which we are going to use in the demo, the content which I've showed is available on the GitHub, and the link is available on the uh, on the slide. Now we'll basically go jump into the demo section, and after the demo we can have the Q&A session. Let me get the my code screen. So here's the repository which I was talking about. I have cloned it and opened in the VS Code ID. You can use any ID which you like. So here, what we have is like we have the bucket.tf where we are defining that we want a Google Cloud Storage bucket. Then the name should be this, which we are passing through a variable called bucket underscore name, then the project, location, whether we want to do a force destroy, which storage class, labels, etc. And these variables are all defined here. So if you see like the bucket name, I generally try to put a description, which I feel very good, so that anyone else is using this module can understand what's the use of this particular variable. And if you want to provide some default values, so you can say by default is equals to the value. So for example here, by default, I'm saying force destroy is false, or by default the storage class is standard, etc. Then the output. So once the resource has been created, what type of the values I am exposing, which can be used by other Terraform code or on the screen. Then the README, uh, which links to basically okay what like basic information, like what version it is compatible with, what are the input variables, what its type, any default value required. This is in the markdown format. So once when you have on the GitHub, you will see in a very nicely formatted way. And then use how to use this module. So basic invocation, then what are the outputs and change log, etc., etc. Then in the examples, for this, I've given two examples like creating a GCS bucket with the versioning enabled and with the no versioning. So let's just take with the versioning. So here, what I'm saying is like I'm calling a module and I'm naming as a storage, providing a source, which is a local path saying like, which is 2 level up the directory, and then providing the bucket name, project ID, label, and just saying the versioning is true. When I run Terraform init plan and apply from through this directory, it is gonna create the storage bucket uh, with the bucket name, project ID, etc. So, and then for the test, again, I have this the fixture where I'm defining the code, like what I want to create or what type of storage bucket I want to create, like the bucket name, project ID, any labels I want to give, and the variables I'm defining in the variables.tf. And in the integrations, I'm defining a control where I'm saying like what type of test I want to do. So for example, first of all, I'm getting a bucket name. So once the Terraform outputs this bucket underscore name, this control will pick that up. If it does not pick, I'm just saying that check the default value, which is my storage 34567. You can leave the default value as blank as well. The interesting part is here. What I'm saying is this is the first test where I'm saying ensure GCS bucket is available and has versioning disabled. What it is gonna do is once when this test runs, it will first check that this bucket exists, and then it will check that whether the versioning is enabled is false. If the versioning is enabled, then this test will fail because this test expect the versioning to be in a disabled format. So let's now move forward and maybe we run this code. So as we saw, what we will do is we will first run the kitchen create. Another important thing, as these are all like the inspect, Terraform, kitchen, all these are Ruby based. So that's why we have this gem file where we say like what version we are expecting and etc. And if you don't have Ruby installed, please make sure that you have a Ruby installed on your uh, workstation. For this particular code, I have a Ruby 2.7.4 installed on my local system and it is working fine. After Ruby, you can have a bundler which will basically get all the required libraries or dependencies, etc. It's similar to pip in the Python world. So what I will do is I will first run, sorry, I will just run with the bundle so that if there is any dependencies required, it will get it. So I will first basically do like a kitchen create. What it will do is it will start the kitchen. It will initialize. What it will do is it will initialize the Terraform code. So you can see like it's doing Terraform init. It is getting the module. It is initializing the backend, etc. So it says that the test kitchen is finished. So it has created successfully. Then what we can do is, sorry, there's a lag. So what we can then say is kitchen converge, which will start running the Terraform plan and apply. So we see that it has started the Terraform plan, which says to create resource, which is a Google storage bucket with all these values and applied it. So once the apply is complete, it says that resource is 1 added, 0 changed, 0 destroyed, and these are the output which we define, right? And then to run the test, what we say is kitchen verify. Once we run a kitchen verify, it will run those in the inspect GCP test against the GCP infrastructure which we have created so far. So it's taking a little bit extra time. So we say that, okay, it's trying to read the Terraform input variables and the output variable from the kitchen instance state, which means like the Terraform state file created by the kitchen converge to get all the values. In this case, we are only getting the bucket name. And then it just says that, okay, it's running the default, the package. It's running the default package. Under that, there are two rules saying that the bucket is expected to exist, which exists, this bucket exists, and then the bucket versioning should be disabled. So it says that bucket this versioning enabled is expected to false, and which is actually false. So this is how it says that, okay, one successful control, there's no failure, etc. If something fails, then obviously it will show as a failure. I will show you a failure case as well. I will change the control, but before that, we can also just verify that this bucket exists by running the gsutil command. So if I just run gsutil ls and then just to grab on kitchen, I should see the bucket name. So I see that workshop demo kitchen test 3894, which exists. So which means the testing is working fine. Now let's just say I'm changing the control. Let's just say that we want is versioning is enabled for that particular bucket. So I'm gonna run this test again. The bucket which we created does not have versioning. So ideally, what this test should do is in this control, we have a two test. The first one should pass because the bucket exists, and the second one should fail because the bucket which exists does not have versioning enabled. And the test expects to have the versioning enabled. So here we see that the bucket workshop is expected to exist, which is green because it's there. But the workshop, which is expected, the versioning is expected to be enabled. So the expected was true, but what the inspect has got is false, which means versioning is disabled. So, so if you have a failure, you would get something like this output where it will says that one successful test, one failure. If there is a single failure in the particular control, the control will be considered as a failure. And this output can also be we can get in the different format like in HTML format. So if you want to just host a web page by running these tests on like a regular basis, you can do so as well. So you can basically monitor your infrastructure changes with the kitchen test as well. So this is what we talked about is like a kind of integration test. If you want to do like end-to-end tests for your application, you can still leverage the kitchen test. You would need to write your own code, or you would need to write your own test specific to application. For example, let's say once the application is up, it should listen on port 443 or maybe port 5555. All those stuff you can do with the kitchen and test it. So that's all for today's session. I hope you guys have enjoyed this demo, and let's move to the questionnaire section. So now it's a time of questions. We can spend some time if you guys have any questions. And to find me, you can look for me on LinkedIn, GitHub, Twitter, or you can read my blogs on my website. Thank you, everyone. Thank you for staying here. Now it's a question time.